So, good morning, everyone, and welcome to the Viva examination of the doctoral thesis presented by Ivan Garrido and entitled Automation of the Thermographic Inspection, Development of Thermogeometric Algorithms for Detection of Pathologies Supported by Machine Learning Strategies. The supervisors are Susana Laguela, Dr. Susana Laguela from University of Salamanca, and Dr. Pedro Arias from the University of Vigo. The examining committee is formed by Dr. Blanca Tejedor from the Polytechnic University of Catalonia and Dr. Eva Barreira from the University of Porto. Before giving floor to Mr. Garrido, I'd like to describe how this event is organized. After the presentation of the PhD candidate, the committee will start a debate in order to ask the candidate any questions they might have and make any comments or remarks. After that, any doctor in this meeting room will be invited to make any further comments or questions on the thesis. After that, the examining committee will move to a different meeting room in order to have the deliberations. And after, let's say, after 30 minutes approximately, we will come back to this room and we will make public the grading for this thesis. So, Ivan, do you know the rules or regulations that apply to this Viva examination?
Yes, I know.
Okay then, so go ahead and you can begin with your presentation. Please, during the whole presentation, I would ask all the audience to mute their microphones and switch off the video cameras.
So, okay. Give me 1 second, please, to change the camera modes.
Okay, don't worry, take your time.
Well, I don't know, but okay, I have two camera modes at the same time. I think it's okay for you. I don't know why. Yeah, give me 1 second. Okay. I switch on the camera. This attempt is the correct one. So, please tell me if it is okay. The image and the voice, the sound, I think is fluid. Please.
The voice is okay, but the image is a bit small in the case of the slides of the projector.
Yeah, yeah.
And you are in shadows, but if it's okay for you, it's okay for us.
Oh, okay. The most important is the slide, so this slide is good, that's why it is okay. Everything. Okay, so good day, everyone. Thank you for the introduction of the jury. And with your permission, I start with my presentation of my doctoral dissertation entitled Automation of Thermographic Inspection, Development of Thermogeometric Algorithms for Pathologic Detection Supported by Machine Learning Strategies. As a start, let me explain a little about my research career. This doctoral dissertation is under the University Doctoral Program in Applied Geotechnologies to Construction, Energy, and Industry. thought by the University of Vigo, Salamanca, working in the Applied Technologies Research Group. In addition, I have given some practical lessons in the area of cartography, geodesic, and photometric engineering in the School of Mining and Energy in the University of Vigo, thanks to one of the education of university professors grants of the Spanish Ministry of Science, Innovation, and Universities that has granted to me before the beginning of my predoctoral in October 2017. Through these years, I have performed 3 different research states. The first one in the University of Laval in Canada, the second and third one in the same university, in the Universidade do Porto, in Portugal, in different times. Here we can see the information provided by the Google Scholar regarding my research profile, where the H index is equal to 8 until today. Here we can see the list of my publications regarding the journal papers. In this new slide, we can see the second part of my list of journal papers. In this new one, we can see the publications, but in this case, to the publications of the conference papers. In total, 12 publications of journal papers, all included on the journal citation, 9 as first author, and 7 publications of conference papers, or in international scientific conferences, 5 as first author and speaker. So let's move on to the explanation of the structure of this presentation. It is divided by 4 different main parts. Each part has a different set of chapters, where the chapter 1 is the introduction section that will introduce the context of my doctoral dissertation and analysis of the infrared thermography in infrastructure inspection, the definition of objectives and the structure of the methodology of this doctoral dissertation. Then, from chapter 2 to chapter 5, each methodological stage is developed and described in this presentation, which 7 of the publications are presented here in this presentation. Finally, a discussion among the published papers of this doctoral dissertation, the description of the conclusions and future perspectives proposed are the objective of chapter 6 and chapter 7 respectively. So let's move on to the introduction section. Nowadays, the maintenance of infrastructure in good conditions is becoming more and more important. Proof of that is the link of infrastructures with the 17 Sustainable Development Goals defined by the United Nations, with the potentials to influence to the achievement of these goals up to 92%. Here, in this doctoral dissertation, the infrastructure classes analyzed the following ones. First one, buildings that provide comfort and habitat to people, heritage sites that evidence the evolution of the humanity and provide cultural satisfaction and economic benefits through tourism, and civil infrastructures that enable the communication among the people, as each physical asset has a different service, different structural components, and different boundary conditions we have in each infrastructure. So, in the absence of a good maintenance in the infrastructure, different surface and subsurface pathologies can appear depending on the service provided and the structural components and the boundary conditions of our infrastructure and the study. These forces can damage the structural health of any type of infrastructure, can prejudice health and comfort of building users, and can increase energy demand in buildings. The most severe ones are analyzed in this doctoral dissertation. That is moisture, cracking, thermal breach, and air infiltration. For that, the use of the most up-to-date inspection techniques to implement the required preventive and maintenance tasks is necessary in order to avoid or reduce the negative consequences of these pathologies. In particular, different thermography has the ability to identify surface and subsurface pathologies based on the different thermal behavior between pathology region and pathology-free regions of our infrastructure under study, allowing, for example, to perform an energy study of a building, to differentiate different types of construction in an archaeological site, to investigate the internal friction in civil infrastructures under different fatigue loads, and of course to identify the above cited pathologies, that is moisture, breaking, thermal breach, and air infiltration. So the motivation of this doctoral dissertation arises from the high importance of infrastructures, the high importance of identifying and even thermal characterizing surface and subsurface pathologies, especially the most critical ones, arises from the benefits of infrared thermography as an inspection technique. Leading for this main objective of this research that consists of the automation of the automatic detection, delimitation of cementation, and thermal characterization of different pathologies in variety buildings, heritage sites, and civil infrastructures. Automatic due to these following main points. The first one, due to the benefits of automation in the interpretation of these results, speeding this interpretation, especially on online inspections, and reducing the possible errors caused by operator subjectivity. Due to the increasingly important role of machine learning models in the automation of problem solving. Automation of infrared thermography, interpretation, infrastructure, and recent topic in the state of the art nowadays. Leading for these three main contributions. The first point consists of following with these three different contributions of this doctoral dissertation. The first one is the providing of software reviews of the most recent infrared thermography acquisition and post-acquisition procedures and infrastructure inspection in the absence of such reviews in the state of the art. Then the second contribution was the development of different new automatic thermal image processing algorithms applied to infrastructures. And finally, the third and the last contribution was the presentation of the first combination of automatic thermal image processing algorithms with machine learning models. Leading for these 5 different specific objectives related. The first specific objective with the first main contribution, and from the second to the fourth specific objective related to the second contribution, and the last and fifth specific objective related to the third main contribution of this doctoral dissertation. So let's move on to the explanation of the structure of the methodology of this research. In chapter 2, we can see that it covers the 2 exhaustive reviews explained before, where the chapter 3 it is explaining the first automatic algorithm proposed in this research, and in the chapter 4 it is proposed in 3 different publications from the second to the fourth algorithm proposed in this doctoral dissertation. And finally, in the chapter 5, it is presented the combination of the machine learning models, specifically deep learning models with automatic thermal algorithms. So let's move on to the chapter 2, specifically with the first exhaustive review published in the following paper. The objective of this exhaustive review, as I said before, it is the study of the most recent infrared thermography acquisition procedures in infrastructure inspection. The workflow as follows. Firstly, the different existing infrared thermography approaches in the data acquisition stage when inspecting an infrastructure is searched and described. As a result, two different infrared thermography acquisition modes are found. The first one, passive infrared thermography, consists of the measurement of the radiation emitted by the body when the body receives thermal excitation equal or less than that generated by the solar radiation. Active infrared thermography consists in the measurement of the emission emitted by the body when the body receives thermal excitation higher than that generated by the solar radiation. Then, the most recent infrared thermography experimental setups, when inspecting an infrastructure, are searched and described according to the type of infrastructure and the corresponding acquisition mode and main objective, as can be seen in this slide. Finally, similarities and differences among the most recent infrared thermography experimental setups are described. As a result, we found that there are a great heterogeneity between the different experimental setups. But passive infrared thermography is the most predominant acquisition mode when heritage sites are analyzed due to the delicacy of the materials, and when the objective is to the calculation of thermophysical parameters that require stable thermal conditions. Meanwhile, active infrared thermography is the predominant acquisition mode when the identification of subsurface pathologies is the objective due to the heat, the higher heat generated with active infrared thermography regarding passive infrared thermography, and when the objective is to calculate thermophysical parameters that require unstable thermal conditions. As for the different artificial thermal exciters, traditional techniques, optical heat sources, and advanced techniques are the more common ones. But where solar radiation is the predominant heat source in passive infrared thermography, especially using this type of natural heat source either during the sunrise or during the sunset for pathology identification, due to the thermal changes reach the top during this instance. As for the type of heating, conventional thermography, steep heating, pulse thermography, and loop thermography are the most common ones. Where, regarding the time of acquisition, infrared thermal camera and the thermal can be placed either on the same side regarding the infrastructure, reflection mode, or either opposite regarding the infrastructure and the study, that is transmission mode. Where when the objective is to identify surface pathologies, pulse thermography and reflection mode are the more predominant in the experimental setup. And when the objective is to identify subsurface pathologies, conventional thermography or routine thermography and transmission mode are the most predominant experimental setups. Finally, we found that the thermal image acquisition frequency and the distances and orientation between infrared camera and the body, between thermal exciters and the body, the values are very similar among all the different experimental setups, where the typical range we can see in this slide. This first structure review was published in the International Journal Infrared Physics and Technology in 2020. So let's move on to the second structure review that was published in this second paper. The objective of this second structure review, as I said before, is to focus on the more recent infrared thermography, in this case post-processing, not processing. Is post-processing procedures in infrastructure inspection. Here, the workflow is as follows. Firstly, again, the different existing infrared thermography approaches in the post-processing stage and infrastructure is searched and described. As a result, again, we have two different modes. In this case, two post-processing modes. The first one, qualitative analysis, is when the objective is to identify or delimit, is to detect the position or delimit or segment the pathology area. And when the objective is to characterize the pathology of the infrastructure or to estimate the pathology depth, the corresponding post-processing mode is quantitative analysis. Then the theory of the current thermal image processing algorithms is searched and described according to the corresponding approach, as can be seen in this slide. Finally, the advantages and disadvantages of each of the current thermal image processing algorithm is described as is described in this slide. In the first point, we found that each thermal image processing algorithm has its own advantages and disadvantages. However, many of them are common advantages, such as the robustness to non-uniformity of the infrastructure temperature distribution, to reflections, to emissivity variations, and to shading. And another advantage that consists of some algorithms have the ability to perform and simultaneous qualitative and quantitative analysis. Unluckily, many of them are common disadvantages, such as the need for a thermal image sequence without the possibility of punctual inspections. Another disadvantage consists of the absence of delimitation of the contours or segmentation of the detected pathologies, and the need of a manual interpretation of the results. This second exhaustive review was published in the International Journal Applied Energy in 2020. So, with the acquisition of the state-of-the-art, we are ready to develop the different algorithms. The first one was published in the following paper, in chapter 3. The objective of this first automatic algorithm consists of the automatic detection and the thermal characterization of thermal bridges in different building facades. For that, different punctual measurements are performed from a mobile ground platform and using solar radiation as thermal excitation. As can be seen, the thermal images are processed with the pixel values in 8-bit format. As for the workflow, it is as follows. First, photogrammetry technique is applied, specifically image rectification process, in order to correct the position, the perspective, and radial distortion introduced by the lens of the infrared camera on each raw input thermal image. With this, it is possible to calculate the pixel size on each thermal image in metric units, and in this way, the width or the height of each thermal bridge in metric units. Here we can see the core of the image rectification process. That it is the equation called as plane projective transformation, where the coefficients of the projective matrix are calculated by 4 control points on each thermal image, whose link dimensions the metric units need to know previously. Here we can see the results where in the upper row we can see the original thermal images. In the lower row we can see the rectified thermal images, where the red crosses are the different control points in this case, in this study. Then two one-dimensional media filters are applied on each rectified image in order to reduce noise. And then on each image, it is grouped different local maximums in different lines. It should be noted that these lines are candidates to thermal bridges. Consist of one line in this line has groups of pixels with the temperature value very different regarding its surroundings. following this assumption that consists in this image, in these graphs, that where thermal footprint of a pathology reaches the surface of the infrastructure, its temperature distribution on the corresponding thermal image histogram will exhibit a Gaussian belt. That is the solution in order to grouping the different candidate lines on each rectified image. Then the different criteria are applied, as can be seen in this slide. In the geometric criterion, two predefined thresholds are applied on each candidate line, considering that the cross section of each candidate line has to exhibit a Gaussian belt regarding its temperature distribution. In the case that not exhibit a temperature distribution, it is discarded as a real candidate line to thermal reach. In the first thermal criterion, one predefined threshold is applied related to the temperatures. Specifically, the difference between each candidate line and its surrounding is calculated in order to, again, eliminate noise, reflections, and shading. And in the second thermal criterion, it is related to the linear thermal transmittance in each candidate line. And you are applying again predefined threshold. The equation of linear thermal transmittance calculation we can see in this slide that it is possible from the meteorological conditions of our area on the study, from different tabulate and formulas values, from the temperature of each candidate line, from the width or height of each candidate line in metric units thanks to the previous application of the image rectification process, and from the temperature surrounding on each candidate line. As a result, an increase of office score equal to 15% is achieved regarding the state of the art. That the state of the art only used the geometric criterion and the first thermal criterion, without the application of the second thermal criterion and without the application of image rectification process. Using the criteria in this optimal sequence. We in total having precision recall and F score values between 55% and 68%. As conclusions, an improving regarding the state of the art is achieved. However, filtering box need to improve the performance metric values and need to improve the robustness of the criteria with less predefined thresholds. This first algorithm was published in the International Journal in Energy and Buildings in 2018. So let's move on to the second, from the second to the fourth algorithm. That all these algorithms, in addition to the automatic detection, have the ability to the automatic delimitation or segmentation of the pathology areas. So let's go to the first one. It was published in this following paper. The ability of this second algorithm consists of the automatic detection of the position, the automatic delimitation of the areas, geometric characterization of moisture in different heritage infrastructures. For that, again, different punctual measurements are performed from a fixed ground platform and using solar radiation as thermal exciter. As can be seen, an academic building, a museum, and cemetery are the surfaces under study in this research. Here we can see the different thermal images processed, that the pixel values are with, in degree Celsius format. As for the workflow, the solution of this second algorithm is similar regarding the previous one. That is, the temperature distribution of the pathology thermal footprint on the thermal image exhibit a Gaussian belt, but it is also considered in this second algorithm that the thermal footprint of the pathology filtration on our surface under study will also exhibit another Gaussian belt, where the smaller, the lowest one, it is always related to the pathology Gaussian belt, because generally the pathology thermal footprint will cover less area regarding the total area of our thermal image under study. So the global thermal image histogram will exhibit a pseudo bimodal distribution. With this new assumption, the different steps are as follows. The new first thermal criterion consists of the adjustment of the shape of each input thermal image by a polynomial equation. With this adjustment, it is counted the number of different maximum peaks. In the case that we have two maximum peaks, it is considered that in this specific thermal image has pathology thermal footprints. Otherwise, it is discarded as a candidate with pathologies. In the case that we have two maximum peaks, the absolute minimum value between the two maximum peaks is calculated. For the purpose of ensuring that the lowest maximum peak corresponds to the pathology region, the following points are considered in this first new thermal criterion. That first, the instant of acquisition of each thermal image, having the infrastructure under heating or cooling conditions caused by solar radiation with the passage of the day, and considering the different physical phenomena that occur in water, that is, evaporation and condensation. As a result, during the sunrise, the temperature moisture it is lower than the temperature pathology free ratio due to the evaporation, and the temperature moisture is higher than the temperature pathology free region during sunset due to the condensation phenomenon. With this, we can ensure that the lowest peak it is belonging or not to the Gaussian belt or to a noise. Then, in the new second thermal criterion, different candidates to moisture areas are grouped on the corresponding thermal image. In this case, group areas are not lines as the previous first algorithm. From the temperature range of the pathologic Gaussian belt, estimated by the previous thermal criterion, by the following processing algorithms. That is, morphological dilation process that consists of a declaration of a binary mask in order to differentiate pixel values that are inside the Gaussian belt pathology and the pixel values that are outside the pathology Gaussian belt pathology. And then the nervy pixels are joined in only one single area. The second algorithm consists of the application of connected component method in order to differentiate the different candidate areas with a different label number, as I can see in this example. And here we can see the result of one of our input thermal image, that the candidate areas are delimited by a red line contour. Then, in the end of the second thermal criterion, the Q and kurtosis values of each temperature distribution of each candidate area are calculated. Q is a parameter that represents the degree distortion of a data distribution regarding a symmetrical distribution. And kurtosis is a parameter that represents the proximity of the tails of a data distribution regarding the tails of a perfect Gaussian belt. The interval values that it is necessary in order to consider a temperature distribution as a Gaussian belt, it is to discard moisture candidate areas with false Gaussian belt, as can we see in this slide. Finally, Again, the image rectification process is applied on our thermal images under study. In this case, in order to calculate the different candidate areas in metric units, as can be seen in this example. As a result, pseudo beam modulation, all the histograms of all the input thermal images is obtained. So the algorithm works well. As for the delimitation part, the performance, again, precision, recall, and first score values are calculated, where the average and standard deviation values, considering all the tests, are represented inside this red rectangle. As for the geometric performance, we can see the minimum and maximum values regarding the absolute error and relative error parameters inside the different red rectangles, where larger the error. Conclusions: improvement. The first thing, both in performance values and in criteria robustness is achieved, and future works need to focus on monitor inspections, subsurface pathology identification, and need to continue in the improvement of the absorption robustness in punctual inspections. This second algorithm was presented in the 27th SIPA International Symposium in 2019. Then let's go to the third algorithm developed and described here, that was published in this following paper. In this case, the objective was consists of the automatic detection of the first appearance of the thermal footprint, the automatic segmentation of the areas from its first appearance, and the classification between harmful and non-harmful of internal water in a heritage element. For that, 5 different monitor measurements are performed, simulating different real scenarios at laboratory scale, from and fixed inspection and using stuff simulating radiation. The stuff applied on the back of our object under study, that consists in this case on a mosaic, where the front surface, that is the decorative layer, is the surface of interest with infrared thermal camera, where the thermal images are processed in this case with pixel values in degrees Celsius. The introduction of water inside the mosaic is performed in 2 different ways. The first one, in order to simulate propagation of internal moisture by means of an internal an internal sponge, that it is connected by a duct, as I can see in this slide. And the second way, introduce the water by means of a closed circuit connected to a water tank in order to simulate the circulation of internal pipes in a building, for example, as can be seen in this slide. As for the test, we can see here in a more detailed way, where all the tests consist of first a heating period applied by the staff with a continuous cooling period, where the last and fifth test, not international water, is performed in order to compare with the rest of the tests. And regarding the rest of the tests, the international water, the international water was in different instances, where the first test and the third test simulate no harmful water to the mosaic, and the second and the fourth test simulate harmful water to the mosaic. As for the workflow, it is as follows: that it is very similar regarding the previous algorithm. First, the new thermal criterion is focused on the first task, based on the transition with the assumption that there is of the temperature distribution shape from no thermal footprint of any pathology to the maximum expansion of such thermal footprints along or the thermal image sequence and the study. In other words, from a normal temperature distribution when no thermal footprint of any pathology appear on the surface of our study to pseudo-bimodal temperature distribution as was the assumption of regarding the previous algorithm. With this assumption, it is calculated the summation of the ski and kurtosis values in absolute terms of each thermal image in our sequence and the study, as can be seen in these different evolutions in these graphs, where on the graphs we can see different numbers that represent the relative maximum and minimum values calculated, and below each graph we can see the percentage slope calculated between two consecutive relative maximum and minimum values. Here we can see an alternative graph that if we focus, if we analyze the percentage values, we can realize that it is possible to detect the first appearance of the internal water effect if we analyze the different percentage slopes, as can be seen in the red bar, in the blue bars of this last graph. Then the new second thermal criterion addresses the second task that it follows with the same assumption of the first thermal criterion. In this case, overlapping the histograms of the different thermal images of our sequence and the study, in order to search for different intersection points on our overlapping histograms. Each intersection point as the pixel value of our contours of our pathologies contours. In order to discard false intersection points related to noise, shading, and reflections, the previous assumptions regarding the instant of the thermal acquisition and regarding the different phenomena of water, that is condensation and evaporation, are considered in this case in order to discard which intersection points are really related to our pathology and not related to false. As a result, we can see some examples of our segmentation process applied in this mosaic, where we are obtaining this average and standard deviation values on each different test, where some poor segmentation results are caused by the high reflectivity index of our tested surface of the mosaic. Finally, in the new third thermal criterion, the third task is addressed, following again the same assumption, and with the calculation of the evolution of the summation of schema cortices in absolute terms of the tests. So, if we focus again our previous alternative graph, if we order our percentage slopes regarding the belonging to the internal water defect from the highest to the lowest one, we realize that the order is different depending on if our internal water is harmful or not harmful for our mosaic, as can be seen in this table. Conclusions: satisfactory adaptation of the algorithm focused on punctual inspections to monitoring inspections is achieved, and future works need to deal with the high reflectivity index problem, supporting with machine learning models. This third algorithm was published in the International Journal Sensors in 2020. Finally, let's go to our last and fourth automatic algorithm that was published in this following paper. This last algorithm The objective of this last algorithm consists of the joint application of infrared thermography and ground penetrating radar for the detection and classification of moisture in interior walls of a building according to its severity level, where our algorithm is, of course, again automated. In this case, with the automatic delimitation of the different moisture areas. For that, again, punctual inspections are performed, but in this case, several thermal images on the same surface in order to cover a larger area as a mosaic of thermal images from a fixed ground platform and using, again, solar radiation as thermal excitor. Here we can see that 2 thermal images are processed on the first internal wall and 9 thermal images are processed on the second wall, where the pixel values are in degrees Celsius format. As for the workflow, again, it's very similar regarding the second and the third algorithm. In this case, however, in this case, the solution of this fourth algorithm, instead of considering a pseudo-Bimonad distribution, pseudo-Bimonad temperature distribution as like the second algorithm, it is considered in this case a multimodal temperature distribution. That it is considered in our opinion, more realistic because we'll have the same number of Gaussian belts on our thermal image histogram as the different type of pathologies and the different severity levels on our surface and the study, because depending on the type of pathology and depending on the severity level, the temperature behavior of our pathology thermal footprint will be different among them. So with this new assumption, the new first thermal criterion consists of the determination of possible Gaussian belt ends in the thermal image histogram. For that, it is search the different relative minimum values and inflection points considered as these possible Gaussian belt ends. Then, in the new second thermal criterion, a mask image is generated for each interval of 2 consecutive possible Gaussian belt ends, and an erosion and dilation process and connecting method application is performed in order to group the different candidate areas. In this case, it should be noted that the morphological erosion process is the opposite of dilation process. That is, the pixels that there are not nervy pixels regarding our pixel understudy. It is discarded as a real candidate area, and it is considered as a small noise, as it can be seen in this example. And finally, in the new third thermal criterion, again, the consideration of the instant of acquisition of thermal images, the consideration of the different thermophysical properties of water and the skew and continuous parameters are again applied in this case in order to discard false candidate areas. It should be noted that in addition to the different thermal criteria, it is also applied the calculation of thermal parameter that consists of the evaporative thermal index in order to differentiate each delimitation candidate areas according to its severity level, as can be seen in this case, in this example, using this equation. As a result, with the previous calculation of our thermal parameter, it was possible for us to estimate the surface water movement on one of our 2 walls under study, as can be seen in this example, in this slide, sorry. And with the joint application of infrared thermography and radar, it was possible to discard any possible moisture signals in the first wall, comparing the different results between both inspection techniques. Regarding the second one, that is the one that was estimated the surface water movement, with the joint application of both inspection techniques, was possible to estimate, to interpret the water displacement between the outside and inside of our bore and study, and to estimate the relative depth of water, thanks to the ground penetrating radar has the ability to detect moisture in deeper layers that is outside of the scope of infrared thermography. Compensating infrared thermography with the ability to estimate better than GPR the moisture on surface layer and on shallow layer. Yeah. As conclusions, an improvement of the absorption robustness proposed in Article 4, that is on our second algorithm for puntual inspections, is achieved. And more information and greater reliability can be gained by using more than one non-destructive technique. This fourth and last algorithm was published in the International Journal Sensors in 2020. Finally, in Chapter 5, it is presented our first combination of deep learning models with thermal image processing algorithms. Specifically, the objective consists of the interaction of latest state-of-the-art deep learning model for instant segmentation with two automatic infrared thermography data preprocessing algorithms to improve the deep learning model training for automatic detection and segmentation of surface and subsurface pathologies, in this case in two heritage elements belonging to the same family, marker tree. For that, four monitoring measurements are performed from fixed inspection and using two different thermal exciters. The first one, flash lamps, and the second one, halogen lamps. That at the end we will have two tests in each on each marker tree on the study. One with halogen lamp and another one with a flash lamp. Here we can see the different surface and subsurface pathologies studied on our marker trees that are very common to marker trees. For that, here we can see the test performed in a more detailed way, where the pixel thermal images are processed with pixel values in degree Celsius format. It should be that all the tests first we apply the heat with the lamps on the back on the front surface of the marker trees, but the only interval of interest for us is the cooling time. So in other words, the cooling period, because the heated time we have the thermal footprint of the lamps, and this thermal footprint is not of interest in our work. Here we can see some examples of the thermal images acquired on different on each test performed. And as for the workflow, is as follows: where first the two automatic thermal image processing algorithms are applied on our thermal image sequences. This one is called as optimized Gaussian model for non-uniform background heating and cooling compensation. With this, it is possible to compensate the non-uniform background heating and cooling of our thermal images, because the nature of the heat distribution on our material is like a Gaussian bell propagation. With this compensation of this non-uniformity of temperature, it is possible to increase the contrast between the pathology thermal footprints and the pathology-free regions regarding our surface and the study, as can be seen in this example. And as a circular algorithm, it is an adaptation of the segmentation step of the algorithm proposed in Article 5 or in Paper 5. That is the third algorithm developed and described it before. It should be noted that the adaptation consists of after the segmentation of the areas of our pathology thermal footprints, it is applied an intensity transformation operation equation in order to increase more the contrast between the pathology areas and the pathology free region on our surface and the study, as can be seen in this example. As for the deep learning model selected, mask region convolutional neural network is the selected one that provides bounding box coordinates, class label, a mask for each object detected in our input image. The reason of this of the selection of mask RCNN as our deep learning model is because it is one of the latest state-of-the-art frameworks for image segmentation tasks. Here we can see the mask RCNN framework. As a result, here we can see two different graphs. On the left, the training, the loss values, the loss values evolution regarding the training data set using as an input the raw thermal sequence, the thermal image after the improvement of the contrast. The improvement of the contrast is belonging to the orange line, and the raw sequence is corresponding to the blue line. And on the right, the same, the evolution of the loss value, but regarding for the validation data set. That again, the blue line evolution is the using as an input the raw thermal image sequences, and the orange line using as input the thermal images after the previous application of our two algorithms. We see the time and the stability of the training of our mask RCNN model is better using after the previous improvement of the contrast between pathology areas and pathology free regions. And if we compare the results of the segmentation of our subsurface and surface pathologies regarding the state of the art, we realize that our combination is better. Okay, it's better regarding other different algorithms in the state, especially in order to delimit the deepest subsurface pathologies. If we calculate the average precision record and score values, effectively we can see that we have close to 100%, specifically between 85% and 99%. If we see the numbers inside the different rectangles. As conclusions, an improvement of the training of machine learning models, specifically deep learning models, with the combination with thermal image processing algorithms is achieved. And the most robust methodology of all the works of this doctoral dissertation is obtained with this combination. This combination was published in the International Journal in Sensors in 2021. Well, let's go to the discussion section. That it is represented the different tables, the specific objective addressed with the different published papers described it in this presentation. That we can see that with the first and second exhaustive review, it is possible to address the first specific objective. And meanwhile, with the first algorithm proposed, it was possible to address the second and the third specific objective. On the other hand, with the second and the third automatic algorithm, it was possible to address the second and the third specific objective. And with the fourth and last automatic algorithm proposed and described, it was possible to address the second, third, and fourth specific objective proposed in this research. Finally, with our combinations, it was possible to address the second, third, and fifth specific objective. It should be noted, but with this combination, it is possible to increase the deep learning model training without the need to increase the thermal image resolution and the number of elements of the input data set, that it is always a very difficult task. As conclusion, this doctoral dissertation presents the automation of the infrared thermography data interpretation to identify and thermally characterize surface and subsurface pathologies in the infrastructure field, given the importance of buildings, heritage sites, and civil infrastructures, given the importance of negative consequences of different pathologies, especially the most severe ones, given the importance of infrared thermography as an inspection technique for infrastructures, given the importance of the automation in the infrared thermography data interpretation. For that, several lines have been implemented, specifically 2 exhaustive reviews, 4 self-developed automatic thermal image processing algorithms, and a new approach that is our combination proposed in the use of machine learning in the infrared thermography field. With the achievement of all the specific objectives proposed, highlighting that the combination proposed in the last paper it is the most robust for pathology detection and segmentation. However, this combination it is only adequate when a high number of dataset elements exist. Otherwise, for short monitor inspections, the more adequate will be algorithm proposed in Article 5. That is the third algorithm. And for punctual inspections, will be the most adequate the algorithm proposed in Article 6. That is the last and fourth automatic algorithm. It should be noted that the assumption of Article 5, that is the third algorithm, is still good, despite following the assumption of Article 4 and not of Article 6, because the assumption of the third algorithm consists of searching for the temperature differences along all the thermal images of our sequence and the study, regardless the possible numbers of Gaussian bands in our thermal images. Therefore, we contribute at social level with the optimization of decision-making, implementation, and conservation actions in infrastructure field, with the help to the inspector in order to maintain and building in salubrious conditions and to rehabilitate it energetically. Future works will need to focus on these 4 main points. The first one, in the continuity of combining thermal image processing algorithms with machine learning models, given the good results obtained in this doctoral dissertation, in order to classify different types of pathologies and estimate the subsurface pathology depth, in addition to pathology detection and segmentation. For this future point, some published works were published up to today, as can be seen in this slide. The second future point will need to focus on the improvement of the robustness of the algorithms of Articles 5 and 6, that is the third and fourth algorithm, in order to further reduce or eliminate noise, reflection, and shading problems. As for the fourth future point, the use of to generate synthetic thermal images is also another objective, in order to increase the possibility of applying the combination of Article 7 to more case studies. Because, as I said before, to train a machine learning or deep learning model, you need a high number of input data sets. For this, the third point, one publication was performed until today, as can be seen in this slide. And finally, the last and fourth future point is focusing on the test of the field of works applied to different classes of infrastructure and types of pathologies at the same time, in order to search for the development of a new universal method. But that's all. And thank you so much for your attention. Any questions on qualification of the jury will be a pleasure to respond. Thank you so much. With your permission, I change again the camera mode.
Okay. Thank you, Ivan, for your excellent presentation.
Thank you.
And now calm down, take a breather, and have a sip of water, because we are going to start the debate, the discussion with the examining committee.
Okay.
We are going to begin with the secretary of the committee. So I give the floor to Dr. Blanca Tejedor.
Hi, good morning to everyone. First of all, I would like to express my gratitude for being a member of your examination panel. Your research is really interesting for our field, especially for the diagnosis and preventive maintenance of infrastructure and heritage buildings. So congratulations, Ivan, for your presentation and your work. It's a good job. And now I would like to comment some aspects with you. Some of them are only comments or observations, and other ones are questions, okay? I think that a flow chart to emphasize the storyline of your PhD thesis could have been added, or I would have incorporated a table similar to table 1 of chapter 6 at the beginning of the thesis to observe the main aim and the specific objective with the respective sections of the PhD thesis, because in the first part of the thesis, you have all the information, and when I finish the thesis, I can see clearer the structure of the specific objective and the papers, and maybe it was better to restructure this, but it's okay. It's your option, so I respect your option.
Okay.
Now I start with a question. In our sector, we have different types of IoT instrumentation, drones, vehicles, portable cameras, and so on. Through your PhD thesis, you develop algorithms that introduce the image ratification procedure to improve geometric analysis and thermal criteria. Did you conduct a comparative analysis related to the reliability of this procedure for each type of instrumentation?
Well, the first algorithm, the input thermal images were from, as you said before, from a mobile platform, from a vehicle when it was running. But except the first one, the rest were from a fixed point. Your comment is a very good point, because yes, probably from drones, the thermal image resolution probably will be lower, right? So will be a good research for the future, right? But I think regardless the thermal image resolution, I think you will have always multimodal temperature distribution of your image. Probably from drones you will need preferencing algorithm in order to remove some noise, because you have a longer distance between the thermal infrared camera and your surface on the study. But yes, that will be a good future point. And in our lab we have the drones, so maybe and probably in the future guide these algorithms. So,
okay, it's only because I saw different approaches with different algorithms, and I thought, wow, if this algorithm applied in a portable camera or in another instrumentation is good or not. Yeah, it's only a curiosity, but
But probably you need some purposing algorithm in order to to reduce sharing reflections, because you are on the surface, no in front, no horizontal. You are in a vertical axis, so yes. Otherwise, I think yeah, probably will work.
Yes, you have a new paper in the future.
Hope that.
How did you arrive to consider the Gaussian bell in your algorithms? In other words, when did you observe that Gaussian bell was the key for the automation of data processing? Or was the work that arise with Sfara, for example, or other researchers that say, wow, if we test the Gaussian bell in our algorithms, that is the key? I don't know if you can explain this.
You mean how I identify this Gaussian bell?
Yes.
Yeah, but yeah, at the end, it's not very complicated algorithm, but the most important is that it's simple and works. It's good. But basically, I search for the best one is the last algorithm. But basically, I search for the relative minimums and inflection points, because if you have to search the ends of our possible Gaussian bells, because the wrapping point between two Gaussian bells will be either relative minimum or either inflection point. Then, when you have the points, you have the corresponding fixed values, right?
Mm-hmm.
So between two consecutive points, relative minimum and intersection point, you have your interval of fixed values. So with this interval, you can create a binary mask equal to 1 and equal to 0. You want the fixed values between the inside the interval. So you have, for example, you have 6 and you will have 3 binary masks. But for example, if you have 4 ends, you will have 2 binary masks. 4 ends, 2 Gaussian bells. So 2 binary masks. And then after that, I always apply a error process to eliminate every pixel joined by the very far from the rest of the pixels equal to 1, right? And then I apply an elimination process in order to retrocede the error process, because okay, I eliminate the small region that are considered related to noise. Okay, so I retrocede to the first step. Okay, and then I always you apply the connecting couplet method in order to differentiate each candidate area on each interval of our histogram. So with this, it is possible to, with the label identification, it is possible to calculate its corresponding skew kurtosis values. In order to, okay, this monster candidate area will exhibit really Gaussian bell. So let's go, let's see the symmetry distribution. But it needs that the skew value very close to 1 to 0, because partial Gaussian bell is a symmetric distribution, and the kurtosis value, okay, it needs the close to zero because if the kurtosis value is equal to 0, okay, the tails of our data distribution is equal to a perfect Gaussian bell. So searching for the state of the art, it is acceptable that candidate area exhibit Gaussian value if the kurtosis skew values are between -2 and 2. So with that, the binary mask, this value equal to 1 are our candidate areas. So with that, after that, I calculate the skew and kurtosis values with the real fixed values, not 0 and 1. Instead, we use the real fixed values. Okay, and we check that the skew and kurtosis values are between -2 and 2. And after that, we can discard some false Gaussian belts, right? That's all. Because if you have the master areas, you have the segmentation result, and the delimitation is the same, but the inside of the area is empty. You only draw the content of your segmentation.
Okay, thank you. Imagine that several city councils want to perform your analysis to enhance the build quality of heritage buildings, because the findings could be interesting to create a urban policy or a guideline at local level. Based on your research, do you think that your proposed methodologies can be implemented by any type of practitioner? What are the main barriers?
But as I told you before, I think it's something simply but works well, and it's an automatic algorithm, so it is possible to use for everyone. Basically you need to create an app, an application on your smartphone. Basically to create an option that here click to input your thermal image, and then you click on the button of process. You have the final result. The fields of application. Well, that's a good question. I think it's possible for every object and the study, but if you use, as I told in the last algorithm, if you use flash lamps or halogen lamps, in other words, artificial thermal excitators, you need to be careful. Only analyze the cooling period, because the thermal footprint of the artificial thermal excitators can mask your possible thermal footprint, especially if you work in reflection mode. But the application, I think, is for every building research, because pathology, the thermal behavior of a pathology is more or less always on Gaussian belt distribution. I don't know in medical applications. I think yes, but maybe for the future.
My question was if, for example, you have a maintenance staff of the city council or something like that, if that maintenance person can click on the button of your application, for example, and can obtain the results without have the complex knowledge about your technology.
Yes, because I have this algorithm. I have an interesting point that consists. It is necessary that consists of. It is not necessary to calibrate the camera, the visibility value and the reflection point, and the reflected temperature and the transmittance. Because if you work, if your objective is only to delimit or dictate, it is qualitative mode. So it is not necessarily previous calibration. So I think only be careful to the reflections and on the shading on your building facade. That is the only key. Only the wording that you need to take into account the inspector, right? I think is the only points that need to take into account the shading and the reflection in order to interpret the results of our automatic.
Okay. Concerning the use of neural networks, what is the minimum of data that is required for the training of your bot and to obtain good reliability? Does it depends on the building element? I don't know, for example, in the case of building management system, if you incorporate a bot, this bot needs 2 years of historical data to work correctly. And in your case, I don't know, if you can explain this, or maybe it's a future line.
Both of them. Okay, but let me explain. The application of mask CNN in the last article was good because for two main reasons. Because in the training and the validation dataset, I have used terminal sequences of both market trees in different instances. So you have two market trees in the training dataset and in the validation dataset, but in different instances of our sequences, but in both datasets. So okay, it's easy for the deep learning model to train. But otherwise, when I show one of the works regarding the first future point, I don't know if you remember well. It was presented in the last CURT conference. I used the master CNN applied on single thermal images belonging to different surfaces of building facades or internal walls inside the surfaces on inside tunnels on pillars of bridges. I remember 100 thermal images, more or less 70% training dataset, 10% validation dataset, and on the remaining 10% on the testing dataset. And with the cross method, I trained the master CNN. Yes, you are right. But the simulation results was so. I don't know what is the minimum of thermal images that you need, but as I told you before, one of my future points will be to acquire more quantity of single thermal images running different surfaces to increase the data set and train one better the master CNN or another one, because actually for mass instance are new deep learning models, but CNN is still good nowadays. So I don't know the minimum. I know I only tell you with 100 thermal images. Well, it's also the simulation results. I know it's not easy. For the reason I propose to create synthetic thermal images with generate adversarial networks. That is one of the type of deep learning model to generate.
Okay. Thank you. Finally, I agree with you that some of your methodologies should be executed in the real-world environment in the future, because sometimes we don't have access to electricity to connect our devices, or the environmental conditions change quickly, and so on. And that's all from my part, and congratulations again, Ivan.
You're welcome. I hope you are better with your injury. And that's all. Thank you so much.
Okay, thank you. And now it's Dr. Eva Alvarez's turn. Go ahead, Eva.
Hello all. Good morning all. Thank you, Antonio. First, I would like to say good morning to my colleagues, member of this board, of course, the audience that I imagine that is supporting Ivan in this big moment of his life. And of course, good morning, Ivan. Congratulations for this moment. It's an important moment in your life, I'm sure. First, I would like to give my regards, my institutional regards on my behalf and on behalf of the Faculty of Engineering of University of Porto to the University of Vigo. I would like to thank the invitation to participate in this public defense. And I must say that it's a pleasure to be here and to discuss such an interesting work that deals with one of my favorite topics, that is ERT. So it is a pleasure, really a pleasure to be here. And And finally, my last introductory words are to Ivan. As I said before, I must give you my congratulations for reaching this point. You have produced such an interesting work, and it's really a pleasure to discuss it with you. And I also must highlight your clear presentation previously done and all the clear answers that you give to Dr. Blanca that were very well. You really answer it very well. So, Eva, I will divide my intervention into parts. I will make some general comments, and then I'll go to some more specific details in the work, in the several papers that you presented here. So, starting with the general comments, I must say that this is a very interesting topic. So the main objective of your thesis was to establish a thematic procedure for thermographic inspection in terms of finding the defect, delimiting the defect, and then characterize it somehow. I must say that this is a very, very difficult topic because, first of all, part of your work is related with moisture, and moisture is never an easy topic. It's difficult to study, even when we are studying using mass transfer concepts. But when we are studying moisture with ERT, we need to study it considering not moisture transfer concepts, but heat transfer concepts. So it's difficult to relate the two. So congratulations by the courage. It's difficult. Then you also deal with something that is relatively new, that is machine learning used for detecting problems and defects in buildings. Machine learning, deep learning is already used, but there's still lots of things to learn. So certainly this is a step forward in this field. I want also to highlight the amount of experimental work that you did. It's never easy to do experimental work. It's always, because here in your presentation, just the good things are shown, but I imagine that lots of not that good things have occurred during the experiments, because I do a lot of research and experimental work, so I know that it's not easy, things don't go as we want, but you have a massive amount of experimental work, and I must highlight this publicly. And I must also highlight the fact that you have lots of publications in scientific journals. These journals, most of them are cited in Journal of Citation Report, so they are very respected journals, and so congratulations for that. You have your research validated and strongly validated by our peers, and that is something very important when you reach this stage. So just two things. I don't know if you want to add something to my comments or say something.
Yeah, that's true. The results that you publish in papers are always are good, no? Right? It's not good. The reviewers are okay. No, try again. So, yeah, but that's right. That's right. It's not totally easy, but thermography is something, in my opinion, very interesting, very beautiful. You can use it's very transversal. You can use in a lot of fields. So yes, for me it was a pleasure to experiment into the different research states in your life. I remember to test the first day I can't find any term of computer pathology. The second one, neither. Third one, neither. And maybe the fourth or the fifth day, yes. But for the reason, I think the most important focal point is to develop an universal method. I think it's a topic up until today. But I think as a recommendation that all the infrared thermography researchers that need to reach. That's
okay.
all.
Okay. So I will start with some more detailed issues regarding your papers, the papers that you present in your work. But have in mind that all these questions is from someone that really enjoy your work, and this question may be related with my misinterpretation of something. So just question, we are just talking someone that has probably misunderstood something in your work. So don't worry and relax. It will be just a talk between colleagues, okay? Regarding your first paper, the paper in chapter 3, the one with thermal bridges, you just said somewhere in this paper that you followed the procedure that you found in another paper that was published by your supervisor, by Susanna, and other authors. So what I would like to understand is what is your main innovation regarding this previous paper? So what have you added that has not been done by the other authors?
Okay, that paper really was my first one during my pre-doctoral period. So in order to start in this work of infrared thermography, I started to study that paper. Okay, that conference paper. That paper only applied the two one-dimensional median filters to remove the noise and to check with an algorithm of MATLAB the local maximum candidate lines with the same assumption that I explained here, but only applied the geometric criterion and the first thermal criterion. With my joining this criteria with my knowledge, thanks to my bachelor degree in energy engineering, I combined this criteria with the question of linear thermal transmittance, where the equation was used from the CTA or the Professional technique. I don't remember the initial of CTA, but it is from a Spanish recommendation of energy rehabilitation of buildings, something like that. So that my added value was the second thermal criterion, that is the linear transmittance equation, because from that book I saw that thermal bridges are always between an interval, right? With this and with the knowledge of my supervisors regarding photogrammetry technique, I have added these two topics in addition to geometric criterion. So that is my contribution regarding the state of the art.
Okay, thank you. I will move. Sorry, I didn't organize that well, my questions, so I'm just looking to your document. In chapter 4, chapter 4 is the moisture chapter, right? It's all about moisture. So the first paper that you published in the conference, it's a very interesting one because you deal with moisture and you is your first approach to automatic detection of moisture in a real case study. So my question is, all the case studies, at least it seems to me that all the case studies, beside moisture, they also have a color change, or because you have mold, or because you have stained areas with the attachment or the lamination of the coating. My question is, did you test, and I think it will be easy for you to answer, but do you think that if you don't have this color difference or this the lamination, do you have more difficult, it would be more difficult for your model to work and to detect moisture or not?
Honestly, I think it will work better because if you have not the color change, the thermal camera is always set in equal to 1 luminosity. So if you have not a change of the color, I think it's better because basically the core of the algorithm is to search for different Gaussian temperature distribution, and the Gaussian temperature distribution does not depend on the color change of your surface. If you remember, one of our experiments on board regarding the ceramic tiles, the white ceramic tiles, the results were better regarding the color motif ceramic tiles. Why? Due to the color change. The color change only mask your your results. So never is good. So all the surface, if it is only one color, better.
Yeah. So these stained areas that are not that are related with moisture but are not moisture itself, is just some noise. Actually, they add noise to the or they are kind of noise or add noise to the image, right? Did I understand well? So
yeah, for the this is not perfect. The performance metrics values.
Okay. So moving forward to the paper where you show the results obtained with the mosaic. So in this work, you use the transmission mode, right? You put the heat source in the back part, in the back of the sample. Did you test the reflection mode? I think you did, but I think you didn't like the results. Am I right?
Yeah, due to the high reflectivity index. The decorative layers of the mosaic will have different inclination of each different small tiles. So the thermal radiation on the front surface, as you have different orientation, you have different poles or regions of internal water due to the different inclinations of the small tiles, the thermal footprint of your stove, because it is the heat is not uniform, the heat inside another is always Gaussian distribution, more or less. So you have the thermal footprint of the lamp. The small tiles had the different inclinations. In addition to that, the front surface of the mosaic we have different colors. The colors change. So yeah, I tested honestly the front surface, but for me, I think it was better on the back, because in this case, I simulate a more realistic scenario, because if you have, for example, in a museum, you never hit the decorative layer because you can't damage due to the high temperature reach on the surface of your decorative layer. So it was simulated a real scenario that instead of hitting inside a museum, you hit regarding the outside of the museum. obviously you need honestly you will need higher and safer. With a stuff it's not possible to fit the wall or using.
Yeah, that was my question about this. This was related with the way you can implement these tests in situ, because sometimes these museums, these buildings have very thick walls, and the transmission mode will not be.
Yeah,
it will be impossible to implement. So perhaps in the future, the reflection mode should also, or a way to implement also the reflection mode should be also studied, because sometimes it's very difficult to use transmission mode depending on the building, of course.
Yes, I know that there are some type of sprites in order to put on the decorative layer in order to avoid these different color changes and and same time in order to protect your object regarding the heat generated by your thermostator. Probably because if you have a metal object, it is possible to apply the induction thermography. The induction thermography, this type of experimental setup. Yes.
I think it's perhaps a future development or something like that. I have also a question here in chapter. Yes, in chapter 4 also. Okay, that the paper where you deal with a wall, the one that is published in Sensors, and the name of the paper is
RFC and GPR.
Yeah, that's it. So somewhere in the paper you just use a scale for ETE values, the values of this evaporative thermal index. So this is, you try to classify the severity of the moisture, right? Did I understand well? So you just use this evaporation rate to try to classify the severity of moisture in the wall.
Yes, because the experimental setup was during the sunrise. So,
yeah. So, but do you think that is an easy task? Do you think it will be a generic methodology? It will be easy to implement? I mean, in the future, someone is going to make this inspection to this building that has moisture. Do you think it will be easy to, based on this ETI parameter, to say for sure that this is a severe problem or a light problem?
In my opinion, yes, because if you see the question, basically you only use the temperature of your moisture area and the temperature regarding the surrounding area, regarding your moisture area. So just you need to be careful with the shading and reflections, and regarding that your property surface of your wall and the study is homogeneous. Okay, it's homogeneous. Have not how do you say the thermal footprint of some reflection. Be careful. Maybe surface with the wall emissivity. Yes, it will be difficult, but typically building materials has emissivity value equal to 0.8, 0.9. So yes, but just this question is, I think, it's very practical, very easy to apply, because just you need the temperature of your pathology area and the surrounding area. So in addition to moisture, I think it is will work well with creating area filtration, for example.
Yeah, but you also said in your paper that this scale level 1, 2, 3, or 4 depends. It's different for each case. So yes. How can I, being this person that is performing this methodology, will know that I will have to check. I will have to do this 4 levels for each case. I will have to that I will have. Did I make clear my question?
No, I understand well. Yeah. For the reason I commented that the last work that it needs to develop a universal method for that for example this case. This 4 different levels was due in order to after check how many numbers of levels need. So after check the results, we decided to estimate for different levels. But a good future line, I think it is to I am all my cases of studies of these buildings range the temperature of my pathology area and my temperature surrounding from from X number to I number. So depending on the range of the temperature variation of my area on the study, maybe taking into account possible outliers inside the range from that. Maybe to automatic estimate the algorithm, the required numbers of solitary, or maybe allowing the option to the inspector to change the number of solitary levels whenever he or she wants.
Mm-hmm. Okay. So my last question is also a question that Professor Blanca has already ask something about that is about this deep learning, this machine learning. It's somehow related with our question. What are the challenges to really implement this and to really use this machine learning in our inspection with ERT?
In my opinion, basically the numbers of elements of your input data, because the thermal image basically is as in an image is a matrix of X numbers and I numbers of different fixed values. I think the challenge is also only the number of elements of input data set. Maybe the image thermal resolution, right? As I told to Blanca before, I don't know if you have the half of the resolution drones would otherwise it is. I think at the same time that is not a problem, because, for example, in this case I applied 2 purpose algorithms in order to compensate the general global resolution of thermal images regarding RGB images. If you think for the image resolution, never will be a problem, because in this case I increase the contrast between some pathology areas, especially the surface areas, in order to compensate a little these disadvantages of thermal images that generally are lower resolution. So I think the most challenge of to training deep learning on thermal images is the quantity of your input data set. So I think deep learning models to generate synthetic thermal images is a good way to throw, because it's very difficult to actually acquire a lot of thermal images. You spend a lot of time and money also.
Okay, thank you for your answers to my questions, and best of luck for your future, that I know that will shine to you. So thank you.
Obrigado.
Obrigada.
Okay, thank you. And now it's my turn. This is Antonio Fernandez from University of Vigo. And first, I'd like to congratulate the PhD candidate for his brilliant presentation and his doctoral work. And I'd like to extend my congratulations to his supervisors, Dr. Susana Laguela and Pedro Arias, and also to the coordinator of the PhD program, Dr. Enrique Lorenzo, because the work or the contribution of the supervisors and the coordinators is often undervalued, but I think that their contribution is essential for the thesis to happen, the thesis to be possible. And now I'm going to ask you a few questions. Some of them has already been asked by Eva and Blanca. Don't panic, because I don't have any negative comments or remarks on your work. I'm just going to ask a few questions out of curiosity.
Okay.
So when you were describing Article 3, Chapter 3, something piqued my attention. You mentioned that you use two one-dimensional medium filters. Why did you use two one-dimensional medium filters rather than one two-dimensional medium filter?
Wow, it's a good question. As I told before, I followed the previous conference paper of this group, as they used two one-dimensional medium filters. So okay, I again apply in my work. But basically, I think that the use of two different one-dimensional media filters instead of two-dimensional media filters is because the thermal behavior of thermal bridge is different if the thermal bridge is vertical or it is an horizontal orientation. They used one-dimensional filter in vertical way in order to remove the noise for the horizontal thermal bridges, and the horizontal one-dimensional media filter to the noise surrounding regarding our vertical thermal bridges. So I think that is the reason of using the different one-dimensional filters, because thermal bridges typically are their orientation is either vertical or horizontal orientation.
Did you find any difference between using the two one-dimensional filters approach and the one two-dimensional filter approach?
I didn't check, sorry.
All right.
Was my first, so come on, I need to publish the first paper fast. So.
Because I think that there could be some differences depending on the direction that you use first. If you first vertically use the vertical filter and then the horizontal filter, the results can be different than if you reverse the order of the filters.
But let me explain the following point. After that, in order to remove noise, it was used always the bilateral filtering technique.
All right. So
this moving filter, I think works better because it smooths the intermediate values of our thermal images, and at the same time keep the edges of the possible objects on your thermal images. After the first one, always I used bilateral filtering technique to the knowledge that I consider better, more regarding the one-dimensional filtering.
All right. The next question, maybe that I missed something in your presentation, but I'm going to ask it anyways. In the description of Article 4 in Chapter 4, you mentioned that the skewness should be in between the values -2 and 2.
Yes.
And the same applies for kurtosis. Right. There's nothing wrong with the skewness because as a value of 0 means that the distribution is symmetric. A positive value for the skewness means that the distribution is skewed to the right, and a negative value that the distribution is skewed to the left. But in the case of kurtosis, the value of a Gaussian normal distribution for the kurtosis is 3, which is out of this range. So why do you impose this condition of being between -2 and 2?
Basically, the reason was if you, I don't remember the name, but there is an algorithm that you can calculate the kurtosis depending when how do you want which is the reference. Basically, it's such as you say, but the algorithm that I use in Python, the result of the kurtosis calculation always rest means free regarding your result. So that's right. When the tail is equal or similar to Gaussian belt, the kurtosis is equal to 3. But in order to keep the same reference regarding the kurtosis skew range, I always make a difference of my results -3. In order that kurtosis indicates that it's equal to 0, it's meaning that really it is kurtosis equal to 3, so it is a perfect Gaussian belt regarding its tails.
All right, I was suspecting that, but I simply wanted to make it clear. So in Chapter 5, the description of Article 7, you mentioned that you have used a mask RCNN. And my question is, did you use transfer learning or did you train the network from scratch?
Okay, so that is a good topic. I think it's good for infinite thermography because you have not a lot of open sources. So transfer learning, yes, of course, yes. I used in this case. I used specifically. I used the weights obtained by Masker CNN after its training on the Coco dataset. Challenge, some type of challenge, Facebook group, Google staff participate in this challenge. Luckily, these ways of after the Coco training was open source, or I used this way as before the training, right? Otherwise, probably the simulation result be worse, of course.
So you have used a pre-trained network, and maybe that you have tweaked some or made some fine-tuning of the parameters.
Yeah, I changed all the weights of all the layers. Also, the ResNet, all of them. Yes, specifically in order to because the Coco challenge was training applied on visible images, 3 channels. 3 images is just a single image, like a grayscale image. So yes, I had to train all the weights of all the layers of this deep learning.
All right, and I would like you to tell us about the tool set that you have used to apply the deep learning Did you use PyTorch, TensorFlow, Keras? What were the tools that you used, and what are the underlying reasons for choosing those specific tools?
Okay, I used TensorFlow rare Keras library, basically because the open source that I used the train weight, also the code was uploaded in that web page. What was the reason in order to use TensorFlow and the Keras libraries, because if the guy that uploaded this code with this library, these libraries, I think it's because he decided the best libraries for Max SNN. And later I trained on the FastGap platform, the Center of Supercomputation of Gaussian. I don't know if you know, but FastGap has modules focus on TensorFlow and Keras libraries, so it was bad without any problem to train on that service and on that platform. That is the reason of the use of this type of libraries.
All right. Now people is moving from TensorFlow to PyTorch. I think that this is good to know. It's a recent trend. Have you made your code available in GitHub or whatever repository?
Not yet, but in the future I will upload some codes. But basically, in my case, the most important is the preprocessing algorithms, because in the machine basically I have adapted the input and the output of the machine.
All right. How do you assess the viability of integrating all your research in a commercial prototype? Did you study the possibility of transfer your research to industry?
Not yet, but will be a good point in order to make a new patent. But maybe in the future. Now, after today, just I have concentrated to the research field without to see the commercial.
In particular, I'm interested in two aspects. First, would this prototype be expensive or affordable? And second, would it require highly skilled personnel to handle this kind of prototype?
As I told before, is all of them, including the combination proposed, work in an automatic way. So just the inspector needs to understand which type of input required to work your algorithm. Maybe to adjust the code you need. It's required the format of your outputs. Maybe some guidelines in order to it is what this algorithm works well if you all have not a lot of change colors, have not a lot of reflections, or only applying on the cooling period after artificial thermal exciter application, something like that. It's possible, very practical.
All right. I don't have any more questions. I just like to mention something that I missed to comment on at the beginning of my intervention, which is the fact that your work is supported by a large number of papers published in indexed journals and international conferences. That's a good added value. And also, I think that your stays in research centers at foreign countries is also an added value. and of course the high number of international co-workers. So congratulations once again, and that's all from my side. So as I said at the introduction of the BIVA examination, now if there's any doctor in the meeting room who wants to add some further comments or remarks, you are welcome to do it.
It is lunchtime.
All right. If there are no further comments or remarks, we have finished the presentation, and now I'm sorry, Pedro Arias want to say something.
Yeah. Hi, Antonio and everyone. And I was waiting for after the questions to make a short intervention and relative to this process, right? First of all, I thank to the jury, to the Dr. Eva, Blanca, and Antonio, and to be part of this jury, of this committee. Thank you because I know that all of us has a lot of commitments, and you has dedicated time to be part today and previously to read all the work of Ivan. And thank you for that. I appreciate. And as well, I want to highlight my relation with Ivan was very nice relation in these years. It was a very pleasure for me to work with Ivan along this time. I know to Ivan from the Ivan was finishing the bachelor degree, and until today was many years working together, and it was a very pleasure. And just to say this, to add these short comments, and that's all from my side. Thank you, Antonio.
Okay, thank you, Pedro. Any further comments or remarks from any doctor in the meeting room? All right, so now we can consider that this presentation is finished, and it's time now for the committee to move to a different room in order to carry out the deliberations. We have a few forms to fill in, and we will be back as soon as possible, but I think that it will not be earlier than 1:30, right?
Okay.
So see you later.
See you.
All right, this is time for me to announce that the committee has unanimously decided to award you with the highest mark, excellent or sobresaliente in Spanish. Congratulations once again. Welcome to the club and enjoy your day.
Thank you so much, Antonio, and Blanca and Eva, for taking this opportunity to discuss with you my research along these last 4 years. Yeah, good experts in Frederick Murphy, Blanca and Eva, good experts in best processing, Python, Antonio, for this good experience. It was a pleasure. I felt very well with you these 3 hours. Thank you for your attention. Thank you for spending a lot of time to read all the long document on my the doctoral dissertation. I don't know. I think now is the time to take greetings to everyone. No, it's not good. I think so. Thank you for all the audience for this special day for me. Very. It was difficult, but at the same time, a nice experience on these 4 years. You know, it's not work on one day. You know, we have the test a lot, change the experimental setup a lot. I don't know. You get a lot of reviews of the editors or to organize your submission of paper. You see what the hell happened here. I don't know, and write the papers. It take a lot of time to to clean the code when you code in Python. What you don't know when suddenly broke the code. So, of course, thank you so much to Pedro and Susana to support me during this unforgettable period in my life. With your suggestion, recommendation, what I need to change to do now, especially Susana with their recommendation of technical points in the paper or in the code, and to check about my English writing on the papers, very important. I think I'm not here, but thank you so much for my colleagues of the Geotechnology Applied Research Group. We have pinchers, and drinks and cakes, and later in the laboratory in 220. Thank you so much for my colleagues of Canada, the University of Laval, Xavier Maldag, Clemente Ibarra Castanedo, my colleagues, my Chinese guys, Tianfang, Lingier, Puyu, Dong Pang, Jorge Rasto, that was the owner of the first purposes algorithm of the combination paper. Thank you so much, Eva, to accept me in your research stay. Of course, my family, it is the most important thing of this life. If it's your family, you are not nothing in your life for supporting me, especially mentally, because these 4 years there were some hard days where that the situation was horrible. That it's not, it was not possible to come forward because you hadn't fixed some solutions. It was the most important. My parents, my cousins that are here, and of course my girlfriend that support me every day in my home. And with your permission, I would like to say this last sentence in Galician, because I can't, not understand English. So it's okay for you. Nada, dar as grazas a todos, a toda a xente do grupo, o meu lector da tese, a vos, o tribunal, a xente que me apoiou en Canadá, a nosa delegada, os colegas chinos, me acolleron de forma moi maravillosa no departamento de estudantes, na residencia de estudantes que estivemos, a Eva por recibirme tamén aí no Porto, dar as grazas a miña familia, porque quería dar a oportunidade de que non solamente había que facer presentacións a xente que estaba unha tese, sino aos nosos pais, a nosos primos, a nosas mozas, a nosas mulleres ou maridos, polos traballos que fan no día a día no mundo laboral, polo apoio tan incalculable que se fai ser mellor persoa, ser mellor investigado, porque señores non seríamos capaces de publicar papers e inventar ciencia ni nada por el estilo. Vale, sin máis, pois, eso era todo. Moitas gracias pola... Thank you very much for your score. Today will be always unforgettable day. Thank you so much. I hope we have future collaborations, especially with you, Blanca, and Eva, always. Very that is a very beautiful, interesting research topic. Thank you so much. Graças a todos, muito obrigado.
Parabéns, Ivan. Foi ótimo. Parabéns. Muitas felicidades. Oh, congratulations. Lots of luck for the future.
I think that we can dedicate an applause to Ivan.
Yeah, sure. Well
Because
done.
Okay, then. Thank you, Ivan, for your touching words, but I'm afraid that this Viva examination has to come to an end. Thank you once again for the rest of the examining committee, and thank you for the audience for joining us today. I hope that you have a relaxing Christmas break and a Happy New Year. So this is all from my side, and bye-bye.
You too. Merry Christmas for you, everyone.
So,
Yes.
bye-bye.
Bye.
Buena suerte. Adiós.
Gracias. Chao. Chao.